I want to thank everybody for joining me today with a really cool discussion on two things that I love, which is rockets and simulation. And we're going to talk about this student rocket competition and how they're using simulation to propel design. And we'll get some more into that as we get going. But first off, we want to do a little bit of introductions. And my name is Eric Miller. I'm one of the owners here at PADT. I'm a principal and co-founder here at PADT. I'm a user of simulation now for over about 30 some years. You can my bio is, of course, the co-owner, as I said. I got my BS degree back in 1986 at UC Berkeley and co-founded the company in 94 with two of my friends. I do a lot of simulation, 3D printing, and small business management stuff. I'm lucky enough to write and speak on those three topics as well. And I'm very active in our local startup community here in the Phoenix area, across the Southwest as well, and all sorts of high-tech stuff. And besides all that stuff I do with investing and mentoring, I sit on the board of several tech-related organizations. I'm the chair emeritus of the Arizona Technology Council Board of Directors. And I was a user of Flownex back in the day, so I kind of remember how to do it. So we're joined today by two of our engineers here from PADT. Miles Atkins is our lead simulation engineer, and he's not wearing his hat right now on the screen, but he's the guy without the hat on. He's a team leader for our simulation engineers here at PADT. He's originally from Minnesota, and he holds a BS degree in mechanical engineering from Iowa State University. His experience includes medical device design, renewable energy system design, gas turbine design, and analysis. His role at PDT, what he does here is he supports the engineers and analysts working on next generation of nuclear reactors, space propulsion systems, which we'll talk about a lot today, and a lot more. When he's not running complex simulations, Miles can be found in the wood shop working on his latest project or on the golf course practicing a lot on his short game. He needs that. So Chris Sattini joining us. He's also a simulation engineer here at PADT, and he does application and support. He attended NAU, Northern Arizona University, for his MS in mechanical engineering, focusing on medical device design. So Chris is now focused on helping engineers get the most out of their thermal fluid simulation, which is what we're going to talk about today. So if we go to the next slide, we're going to talk about the gentleman that's really helping us set all this up and everything, Adam Trumpour, and he's the CEO of Launch Canada. So he's a rocket and gas turbine propulsion professional with a broad involvement in the industry, and he is a turbomachinery designer and systems integrator at Pratt & Whitney Canada. Now, I was from Garrett, so that was our competition, but we'll get along here as things go along. And founder and partner of Continuum Aerospace, a small company that's devoted to engineering consulting and developing innovative rocket propulsion systems. In his spare time, Adam is heavily involved in liquid propellant rocketry activities, mentors student rocketry teams, as we're going to talk about, and works tirelessly to advance the cause of entrepreneurial space and rocketry in Canada. He served as a technical advisor for the Base 11 Space Challenge rocket competition and co-chaired its Safety Council and leads liquid rocket launch operations and flight safety for Spaceport America Cup, for the Spaceport America Cup. He's the founder and president of Launch Canada, an organization founded to support and advance grassroots experimental rocketry in Canada, which runs the leading rocket engineering competition in Canada and has consulted with multiple government and private organizations and on matters related to space launch, propulsion, and safety. Adam earned his bachelor's degree in engineering science, that's aerospace, at the University of Toronto, and his Master of Applied Science in Aerospace Engineering at Ryerson University. So we really want to thank Adam for all the things he's done. I wish you were doing it when I was in school, because I would have definitely volunteered for this instead of the concrete canoe with the civil engineers. So this would have been a lot more fun. Let's talk a little bit about the students. Do we have bios for the students as well? Or are we?
Yeah,
we do. Okay, great. So we're joined. So the first team we're going to talk about is the Metropolitan Aerospace and Combustion Hub, the MACH team from the Toronto Metropolitan University. And Ken Kubica is not able to join us today, but if he was able to join us today, he's a second-year aerospace engineering student at the university there and the co-captain and principal integration engineer at MACH. And Shivesh Maharaj is the co-captain. He's a fourth-year aerospace engineering student at the university and co-captain and principal fluid system designer of MACH. The next one here. And Alex Supaya is a chair. So we're going to move over to I'm changing teams here. Purdue Space Program, so PSP. And Alex is joining us. Alex Supai is joining us. And he's currently a fourth-year engineer in the Purdue Aerospace Engineering Program. And he's been involved in the Purdue Space Program Rocketry Club since his freshman year and is now the thrust chamber responsible engineer. That's what RE stands for, I just figured out, for PSP active controls. His experiences in fluid structural simulation, propulsion design, and research. And Stathis Kokifis is the propulsion team member. He's a freshman engineer major interested in aerospace. Aditya Nar is also a propulsion team member, and he's a first-year student as well, planning on majoring in aerospace engineering at Purdue in the School of Aeronautics and Astronautics. And Atharth Batter is also a member of the team. He's from Dallas, Texas, and he's currently a student there at Purdue with everybody else studying the aerospace engineering thing. He joined the program, the space program, in 2024 as a way to get ahead in rocketry and mark his progression into the space industry. And he wants to push to new heights, and he's found working propulsion and fluids, which led him here. And he's really excited to see what's next, which I think we all are. And then I don't know if we have a slide. Yeah, we do. Okay. So Grant Leslie, he's here with us in Phoenix, Arizona at ASU Luminosity Lab. And he's a third-year student at ASU studying mechanical engineering while working at the Luminosity Lab. If people don't know what the Luminosity Lab is, we won't get into it in detail, but it's a really cool thing. Go Google it. It's really cool. And it basically is doing interdisciplinary work for research projects there. So he gets to work on a variety of projects, but he serves as a project lead for Aegis, which is a lunar inflatable landing pad. Another thing you should look up. It's super cool. And it's their submission to the NASA 2024 NASA Big Ideas Challenge. So kind of a neat thing there that they're doing. So I think that's everybody, right?
Yep.
Okay, great. So, the first thing is, why do we care about this, right? Why do we care about space? Why are we talking about this now? Why is space so important? And I don't know if either Miles or Chris want to I know you guys have been kind of thinking about that, and some data is pretty amazing. And the thing that I saw looking at Payload, which is a daily newsletter on the industry, is the number of launches in Q1 was insane. And I think you've got some data also that kind of talks a little bit more about that.
Yeah, and I mean, we've also been seeing the big rocket launches in the evening. If you look,
In Phoenix,
kind of
yeah.
west out of the sky, you can see them coming up, which is really cool. And I mean, I can remember too the first time that I saw the Skylink satellites going across the sky. I was out backpacking in northern Arizona with some folks with the backpacking club in Phoenix, and it's like it took like a minute for these guys to like gather what it was. Like, is this aliens? Like, what's happening here? It's like, no, that's the SpaceX stuff.
Yeah,
But yeah, numbers wise, I mean, it's projected to grow the space economy to like $1 trillion by 2030. In 2023, I think the spend was around 447 billion. And it's just gone up and up. I think active number of satellites today is around 5,000, but we expect that to triple to like 15,000 or so in the next 5 or 6 years. So it's really exciting. It's really growing. I think it's also, we've seen that there are less folks that are graduating today with engineering degrees than there were 4 years ago. So, I think the work that Adam's doing, especially with like Launch Canada, to get folks excited about this topic is incredibly important.
And hit the ground with some real world experience. And of course, you can't get into space without propulsion, right? And without a rocket. So it's really, really an important thing. So I was just at a summit here in Arizona. We do every year on the space industry, and about to head up to the Space Symposium, which is the big gathering of everybody in space. And the big change that I've seen is when we went 8 years ago, people were talking about when I launch, when my satellite goes up, when my experiment goes on the ISS. Now, when I see them, they're like, I'm launching in 3 months, or I got to get ready for my experiment to go up, and it's going to go on the ISS. It's time. It's happening. It's not planning. It's happening. So it's pretty cool. Another thing that we talked about with the summit is how important space is from both a national security and a commercial standpoint. And so we got to have the rockets to get up there. We got to have people know how to design rockets to get up there. So, um, and I will add, one of the cool things about being in rocketry is you can say, no, actually, I am a rocket scientist, and this is the way it's done. So it's a nice thing to be able to say. Adam, do you want to add anything to that? Because you're in the middle of it all.
Yeah, no, I mean, I think you really kind of said it there. The way this industry has been growing and transforming over the last 10 or 15 years has been pretty dramatic. And I mean, I remember when SpaceX first came on the scene, and for many years they were pretty roundly dismissed by almost
Yeah,
everybody, right?
yeah.
People didn't take the idea of commercial rocket companies seriously at all.
Mhm.
Um, Fast forward a few years, we kind of know how that's played out, and it. I find it's often the case that, something might seem impossible until suddenly it's not, until the first person actually does it. And SpaceX kind of played that role for
Mhm.
entrepreneurial rocketry.
Yeah.
But what that's led to is this massive surge of interest, really all over the world. And I've been seeing kind of the Canadian side of that in particular, where it's been playing out in maybe a slightly unique way.
Mhm.
But just the growth of this has been pretty stunning.
Yeah, it really is impressive. Um, so let's start with a little bit of background on the whole concept of what is Launch Canada, and maybe a little bit about the impact you've seen that it's had on students.
Yeah, sure. So, like I was saying, about 10 years ago in Canada and really all over the world, we started seeing this surge of interest in rocketry, particularly by university students.
Mhm.
And this is, I think, a genuinely global phenomenon. There are rocket teams all over the US, Canada, Europe, Latin America. It's really gotten big. And it was partly a series of rocket competitions that opened the door to that. Kind of the one that started it all was the Spaceport America Cup rocket
Mm,
competition, and its predecessor, the IREC competition. And for speaking for Canadian students, that was the first time that they had a clear pathway to be able to engage with this, because there was no such thing as a Canadian rocket company, really. There
mhm,
weren't really those opportunities. But we initially saw a couple Canadian university teams get started to take part in that competition. And from the very beginning, it turned out they were incredibly good at it.
excellent.
And so I this was not a thing that was around when I was in school,
Mhm.
but as somebody who had kind of been building and testing rocket engines in my spare time for a while and building up these skills that aren't so common here, I initially found myself mentoring many of these individual teams and helping to teach them how to not blow themselves up. And as I kept going forward with that, and the team sort of kept multiplying, I was just reaching the limits of what I could physically do as one person in my spare time. So I started Launch Canada as a not-for-profit in 2019 to try to do this in a more coordinated way and sort of pull together and support this community as broadly as possible. And the initial focus was on trying to put together a Canadian rocket competition
Mhm.
so that we could make this a lot more visible here in Canada and create more opportunities for more people to do this. But very quickly, the goal kind of broadened, and we're at a really interesting time in Canada where we are starting to see the beginnings of a domestic space launch industry. We've got a private company called Maritime Launch Services that's building an orbital spaceport on the East Coast in Nova Scotia. And that sort of prompted a lot of work by the government to figure out how to authorize orbital rocket launches.
Yeah.
But there are knock-on effects to this, and we've seen a number of startups get set up in Canada working on developing space launch vehicles. And the students have really been kind of at the center of all of this. We've got a couple launch vehicle startups now. Every one of them was either founded by former members of student rocket teams or else hires almost exclusively from those rocket teams, because right now that's where you're going to look if you're trying to find that expertise. So with Launch Canada, we were kind of recognizing the value of these student learning experiences, because at the end of the day, you've got student rocket teams who are doing incredibly sophisticated work. This isn't concrete canoe. This is kind of a step beyond.
Yeah, quite a bit.
Not that there's anything wrong with concrete canoe. Those are really cool too. But rockets and launch have always been this really high cost corner of the industry, because ultimately, like, this is really high skill, high precision manufacturing. And part of the reason why we didn't really see any commercial rocket companies succeeding until SpaceX was that it just costs a lot of money to do it. And unless you've got the resources to get through, all the inevitable failures as you work your way towards those successes, it's really hard to make a go. But these students are able to do things for orders of magnitude lower cost than even the most aggressive startup ever could. Oh. And this is what happens. We've got a bunch of like super dedicated people who are just putting their free time into something, right? And they can leverage sponsorships and university facilities and all of these things. So when we were getting Launch Canada going, we kind of recognized that this is actually a really interesting way to approach innovation and skills development in what is normally a really high cost area. So we really wanted to try to support and unleash that as broadly as possible. And at the same time, make sure that students are connected to the resources they need to be safe and successful. And of course, Purdue has been building rockets and testing them for generations now, but not a lot of universities are in that position. So as you might expect, when you get university students going to their faculty saying, hey, we want to test a rocket engine, that's usually going to set off a lot of red flags, because it does kind of scream liability. And even when a school wants to be helpful, they don't always have the kind of expertise on staff that would allow them to. So the other goal with Launch Canada really was to try to get to a place where we could sort of reassure schools that, you might not know this stuff, but your students aren't going it alone. They're actually connected to this broader community of people who do have that knowledge and that background to help them. Cool. So that's sort of what we try to do, and it's been really going interesting places.
It certainly has, and the big takeaway for me is your comment that the domestic launch industry is hiring from this group of people. So that shows that how better could you judge the success of a program, right? That's pretty cool. That's pretty cool. I love that. So let's get into the MACH team. Let's start there with the team there, and We'll start with Shivesh, right? What is your role on the team? What got you interested in space? I mean, why did you decide you want to do this space thing?
Yeah, so I am the co-captain of MACH, Metropolitan Aerospace and Combustion Hub. So as the co-captain and as the fluid system designer, I'm really more so involved in high-level and detailed design for anything that deals with the fluids that our system interacts with. So for a little bit of context, we deal with liquid bipropellant rocket engines. So nitrous oxide is our oxidizer, ethanol is our fuel.
Okay.
So I do all sorts of modeling with software like Flownex to make sure that our sizing is correct. Our system, if it fails, would be able to relieve itself of pressure, go back to a safe state. So that's typically kind of what I've been involved in, as well as kind of chamber design, injector design, all sorts of stuff, both at the high level and detailed design level. What actually got me interested in space, funnily enough, is kind of my experience visiting Florida as a child. So I would visit Florida. I have family in Florida, and my uncle, who's a physics teacher, actually used to launch model rockets with his class.
Oh, cool.
So anytime I used to visit him, I would be launching model rockets. And Florida, being essentially the best place to be exposed to rocketry, is really what set off that interest. So I was able to visit Kennedy Space Center, see the Saturn V. I actually saw a space shuttle on pad, and since then I've been addicted.
That'll do it. So
Yeah.
so one thing that I'm not clear on is, are these gravity fed, or do you have pumps as well on these rocket motors?
So we pressure feed our engine.
You pressure feed. Okay.
Yeah. So currently we supercharge our nitrous. So we use nitrogen pressurant to raise the pressure of our nitrous to above its just natural vapor pressure, and we do a similar pressure feed for our ethanol. That's our current system. We're also developing a brand new system to self-pressurize our nitrous, which is kind of one of the other options when dealing with the nitrous system. So they're pressure fed. Okay. But interestingly enough, through involvement in organization, well, particularly Launch Canada, we actually in Canada have begun to get exposure to pump fed systems, which is very unique, definitely at the undergraduate level. So on MACH, we do pressure feeding, but on Launch Canada, we're actually starting to get into pump fed systems.
Very cool. And as a turbo machinery guy, that's why I asked, right? That's my favorite part. Cool. Good. So what was the biggest challenge that you've run into in the competition?
So I'll have to speak to this kind of anecdotally based on what I've heard, because unfortunately I wasn't able to attend the competition. Okay. But from what I've heard, essentially most of the challenges at Launch Canada boil down to system integration. So it's, of course, really easy to set up your system in a laboratory environment where you have everything right there to use, but that's not necessarily the case when you're going up to the middle of nowhere in Timmins, Ontario, and setting up a liquid rocket system to statically to perform static hot fires with. So essentially, the biggest challenge was, making sure that we have a setup that we're able to transport, that's modular, and making sure that everything is in place to allow for remote testing in Timmins.
Real world. So, and a big takeaway for me is system. I think that was even after all the years that I've had in industry, I have to keep on reminding myself that it's a systems problem. I'll get a good component going, but it all comes down to a consistency problem. That's a really good point. So what are your plans for post-graduation? What do you want to do?
Well, currently I'm interning at Pratt & Whitney Canada. It's a great organization. I love it. So that's kind of my plan to continue on with the company. Potentially moving into more of an analytical field. So currently I'm dealing a little bit more with the operations side of things. So hopefully postgraduate, I get into more analytical work. That's where I'm aiming for. Cool.
Excellent. Well, good luck with that. You definitely got a good start here. It's really cool. Let's move on to the Purdue team. And you guys, I guess, didn't get a chance to participate in Launch Canada. So can anybody that wants to speak up about any of the competitions you were able to take part in as a team?
Yeah, so PSP is the Purdue Space Program. Overall, it's an umbrella org, so we have 7 different teams under it.
Oh, okay.
We represent the active controls team, which participates in the Collegiate Propulsive Lander Challenge. So that's a liquid bipropellant, or I guess doesn't have to be bipropellant, but the teams have all chosen to do bipropellant. But basically a lander vehicle to participate in 5 different challenges. So you have to demonstrate throttle ability, gimbal ability, and then eventually controlled takeoff and landing of a lander. So that's one of the PSP teams. That's the CPLC challenge. But we also have a liquids team that participates in the DPF dollar per foot challenge in Mojave. But we also have the team that goes off to spaceport. We have a satellites team and a hybrids team. Yeah, so each one of them compete in a different competition.
Very, very cool. And again, anybody on the team can speak up to this, but what was the biggest challenge that you or the team you were on faced?
Yeah, at the moment, so we recently completed the manufacturing of our thrust chamber, actually, and a little bit of background about this one. We decided to go for a full regeneratively cooled, gimbalable and throttleable rocket engine.
Wow.
So the biggest issue that we ran into during our design reviews was figuring out how to do regenerative cooling analysis. it was just hitting the drawing board every time. We didn't want to spend too much money with copper because of how expensive that would be, but we knew we wanted to 3D print. So we'd pick a material, we'd do the analysis, it would melt or fail. And then we just keep running through that. We met with a bunch of different engineers. We actually met with a team from NASA who recommended the material that they were using, and then a team from Relativity Space. And so we figured out kind of the correct approach for how to go about this problem, and then come together to, within 3 months, go from PDR to CDR, and present a full analysis. And then now we have a full thrust chamber that we're hopefully going to test this summer. But yeah, that's been a huge banging our head against a wall for a long time.
Yeah, I mean, the rocket science joke works because it's hard. It's really hard, and that's a big step forward to do the regenerative. So did simulation play a role in any of that work or any of the other work you've done?
Yeah, absolutely. We do a lot of CFD for injector stuff. We, particularly with the injector, hand calcs can only go so far. We want to look at propellant maldistribution and pressure losses within the ejector. But as far as the thrust chamber goes, we did a lot of FEA, some thermostructural analysis, see how our margins compare to our hand calculations for our stress and fatigue analysis. And there's a lot of back and forth between, okay, we have these numbers for our heat transfer and our stresses. Let's go to a 3D sim and see, try to pick it apart, see if there's stuff that we can figure out about it that we can't see from one-dimensional analysis. And we ended up learning a lot from that, and it helped with the whole design cycle with, oh, we're seeing kind of different results here. Why is that the case? And then finding a mistake in our analysis and then going back and then fixing different parts and pieces where one of them makes up for the other. And yeah, a lot of effort there. And then Flownex has been an effort that we're bringing up now as we go to hit the test stand. We want to reduce test time, reduce the amount of times that we have to characterize the system, and use Flownex to characterize our engine as like a digital assembly of it.
Yeah,
Are you guys doing any dynamic analysis? Are you, because I saw your presentation a while back on your Toad program, and it sounds like it's got to do some sort of a hop.
Yes.
Is that right?
Yeah. Dynamics, you mean like shock and vibe type of dynamics?
Or just a transient, versus like a steady state analysis is what I'm curious about.
Structurally, we haven't looked too much into that. The Toad vehicle itself is still on the drawing board. We're hoping to hit a conceptual design review either this summer or early next semester. It's still being sized, like how big, how heavy, what the landing legs will look like. But eventually those dynamic sims will need to happen, and we're excited to try to tackle those. Yeah.
Very cool.
That's pretty cool.
Yeah.
Very cool. Wow. Okay. Very sophisticated. Much more than the concrete canoe that we did. It's pretty cool. So, the rest of the team, anything you want to add about using simulation, any challenges you faced that you learned in all these things? Anything you want to share with the listeners?
Sure. Yeah. I'm a third. I've recently joined this team, so I'm kind of working on this one project, and I've been working a lot with Flownex. It's great because it allows us to make changes in a virtual sort of world. And then our plan is to, once we have our Toad set up, we can compare data from testing and hand calcs to what we've created on the simulation.
Perfect. Love it. Anybody else want to share what they're working on?
Yeah, another big thing we're trying to do is because we have like these cooling systems that we're trying to model, and I think that Flownex would be a great use of like we'd definitely use Flownex to model the regenerative cooling like systems of our rocket engine. So that's another project that we're going to do as the deadline for the lander approaches.
Very cool. Anyone else have anything they want to talk about that they've done on this project? Deecha?
Yeah, so I'm also a freshman in Flownex or in PSP, and I just recently joined. And
great,
like at Tharp and Stathis, I've been working on Flownex quite a bit. And I kind of wanted to talk about a couple of the problems that we've seen, and then how we used Flownex to address those problems. So one of them was like a specific problem called water hammer, and which is the surge in water pressure, which occurs when valves are closed too quickly, and it causes the water pressure to rise rapidly. And this is a big problem because it can obviously damage the pipes. And one of the good parts about Flownex, which me, Stathis, and Atharv have been delving into recently, is we've been watching the tutorials to get more knowledge about it because we're all pretty new to this. So Flownex actually has a specific tutorial on water hammer. And what Flownex really does for us is it helps us virtually simulate these issues. And it also really helps us get a general background and sort of knowledge to help address it on our simulation.
Very cool. I love that. I actually have a water hammer in my wall in my bathroom at home, and instead of fixing it, I keep on thinking I need to model that in Flownex. It's really kind of sad. So very, very cool. All right, let's move on to the Luminosity Lab and all the different things that Grant, the team there, is doing. And the thing you guys are working on quite a bit is the infrastructure. I mean, you guys are working on a lot of stuff, but in particular, Luminosity is involved in the infrastructure for a permanent human presence on the moon. I'd really like to hear more about that program because I just think it's super cool.
Yeah, no, totally. This is one of my favorite projects that Luminosity is taking part of. We've been doing the NASA Big Idea Challenge for what, I think 5 or 6 years now. We've done it 3 times, giving ourselves a little bit of breathing room. But this year we're super excited to start working on, that long-term presence on the moon. And part of that is, right, you're sending landers up there. Specifically, we're targeting those CLPS landers. When you're landing on the moon and you're ejecting all of your gases down onto the regolith and basically shooting up a giant dust cloud, it can be really damaging to all of your structures, and you have to land super far apart as to not get these like little shards of glass having like 2 kilometers a second. So in order to combat that, we're doing designs for a landing pad for the moon. So currently we're set up to our current simulations show that we're like a 95% improvement in reducing like the shear stress along the ground. So showing some super promising results for our design. And yeah, we're currently in some initial design phases of we got our proposal accepted about a month ago now. Which was super excited to be one of the 6 teams moving on. And now we're moving into some more detailed design stuff. So getting past just preliminary simulations, and getting some parts ready to be ordered in about a month here. We're going to start kind of converting over to. Yeah, it's a quick process. We've got our mid-project report in a couple months, so we're aiming to have some good stuff to show for it then. But yeah.
Any I don't know if you're far enough along, but any specific uses of simulation you can talk about in that process so far?
Yeah, so a majority of our stuff right now is just doing some CFD, I believe using ANSYS Fluent. So doing that to drive constraints for our system. So other than just the constraints of all the lunar conditions, our other main thing is we got to shove a rocket engine on top of this thing. So a lot of it just taking our initial geometry and getting all the specs for like temperature profiles and pressures and forces on our structure, especially going to the inflatables route. We're going to be doing a lot of simulations for actually looking at each of the individual components to make sure they can withstand all the necessary forces and temperatures. So a lot of that just driving almost every single one of our constraints is going to be driven through a simulation.
Cool.
Yeah, which is cool.
Love it. I love it. So put it on your guessing hat here. When do you think we'll have a permanent presence on the moon? I mean, we're getting close, right? We landed, fell over, but that's better. So when do you think we'll be permanent?
Yeah. So this is a super fun discussion, especially because I'm actually fairly new to all this space stuff. I think it's super cool, all these programs. So it's been super exciting to see. I'm definitely looking for kind of along the lines of all the Artemis missions that are coming up, right? So that like looking at more to like that mid to late 2030s, looking to actually have some like sustained missions up there is really exciting to look into.
Yeah, I'm obviously excited about it, and I'm old enough to remember I may be the only one here to remember the original lunar landing, but I was in like second grade, and yeah, it's pretty cool, and the technology that's already coming out from this is pretty. I can't I don't know what TOAD stands for, but that's going to be really useful for these lunar landers, right? To be able to do this maneuvering and hover and stuff.
And it
Miles, you want to add
sounds
something?
like, yeah, it sounds like there's a little bit of crossover between what Grant's doing at Luminosity
Yeah,
and what the Purdue team is doing,
yeah,
because that's the idea, right? Is that you land on this landing pad and then you
yeah,
do like a hop off so that you're not, causing that big dust cloud that's going to be abrasive and
mhm,
damage your equipment. So that's very
yeah,
cool. Is that
yeah.
right though?
Yeah, no, exactly. That's the current plan in place. While we're not necessarily looking into the whole hop and stitch, no, it's really cool. It's like, I mean, all the stuff that you guys are doing over at Purdue, that's exactly what we're kind of relying on, getting those functionalities in place.
Yeah. Yeah. So I don't know, Chris or Miles, do you want to add anything we've talked to what we talked about? I don't want to underline any points, but
Yeah.
you've worked with the teams for a while now, and yeah.
Yeah, I'll just throw out a comment. It's fantastic to see, how well these teams are progressing in light of the fact that, like Miles said, we're having an exponentially expanding space industry, and to point out or highlight a point that Adam made. It's great to see how student teams can do so much with so little resources. And I think we've heard from all these teams, and from what it sounds like, the ability to switch between simulation, whether that's network level or component level, and the actual prototyping is one of the strengths that I've seen in all of the teams that I've been able to work with. So that I think that's a testament to measure twice, cut once.
Yeah.
These teams have been doing a great job at simulating stuff before they get actual physical products out.
Yeah, it's you learn a lot from what do they call it? An uncontrolled disassembly? Is that the euphemism they use, right? You learn a lot from that, but it's much better if you avoid it, right? If you can use simulation to avoid it, I'm a big fan of that.
Costs less.
Go ahead.
Oh, it just costs less.
Yeah.
We got a shoestring budget.
Yeah. When you're on a shoestring budget, it's so true. Miles, you have anything you want to add?
No, same things. I'll
Yeah.
rehash it, especially, in the last few years with a lot of supply chain disruptions. Like we've
Yeah.
seen folks really lean into simulation because it, timelines get pushed back when you have to wait on materials to ship and to build a test rig just to see, if your predictions are right. And if you can, run a few more iterations, do a few more material studies in that virtual environment, you can save time and you can save money.
Yeah, for sure. How about you, Adam? Anything you want to add with the work you've done with these teams and other teams? And
Yeah, so I mean, obviously, simulation does play an absolutely critical role in all of this. And one of the things that we're doing with Launch Canada right now that Shivesh alluded to is, in addition to the competition, we also see a lot of value in collaborative projects. And one of the things I think that most students realize pretty quickly when they start taking on something like a rocket project is that the real world of engineering design doesn't really look like what you typically learn in school. It's not like a problem set or an exam where you've got a question and a very relatively clear, matter-of-fact answer to it. It's really open-ended. And design is ultimately all about, deciding what your requirements are going to be and then making a whole bunch of choices consciously and sometimes unconsciously that hopefully will lead you to something at the end of the day that meets those requirements. But often when students are going through that exercise, the choices that they make are going to be very heavily influenced by some basic realities of being a student. And usually that includes, very little money, very little time, and relatively little experience. And that does mean that sometimes there's going to be this pressure to kind of end up with the Home Depot rocket that might kind of sort of almost work sometimes. And while there's, that can still be a really valuable exercise, it probably means you're likely to end up with things that are pretty marginal a lot of the time. And trying to make sure that you don't go and, blow up $10,000 worth of rocket because you saved a little bit of money on an electrical connector, is not always a good choice. So the more people can come to understand the trade-offs, the better. And so we're actually working on a collaborative turbopump project with all of our teams to try to kind of show a professional approach to how to actually design this type of hardware. And simulation is absolutely critical. And when you're doing something like a turbopump in particularly, you realize that there are an awful lot of very deep rabbit holes that you can go down for every possible component, looking at bearings, seals, internal flows and leakages, all of these things. There's a lot there. And ideally, you want to avoid having to have too many pumps spontaneously disassemble themselves to gain an understanding of how that system is behaving, right? So we're relying pretty heavily on tools like Flownex to hopefully get us to something that works more quickly.
Yeah, I thought it was interesting. Shivesh mentioned that like Timmins is like a pretty isolated off the grid location, but can you imagine, designing a system that, not is not even, it's maybe going to the moon or going to Mars, like that's even more isolated, and you're not going to be able to do the repairs or run to the Home Depot, right?
You don't have duct tape. Yeah. Are you got to design a robot that goes put the duct tape on, right? So that's actually one of the questions as we're wrapping up here a little bit, because I could talk about this for another hour, but we'll wrap it up. But one of the questions I like to ask is, so if you want to go into rocketry, let's just assume that you're going to pursue a degree. Would you rather work on rockets that go to orbit, to the moon, to Mars, or deep space? Which one? I'll start with you, Grant.
Well, my goal is to do whatever the rockets need to when they get down. So,
okay.
If I had to focus, I mean, I got my first foray into doing lunar stuff, so I got to go with lunar.
Got to lean toward lunar. Okay.
Yeah.
Okay. How about you, Atharth?
I mean, space is just so mysterious, right?
Yeah.
So deep space, definitely interesting. I haven't really thought about it that much, but currently in my lifetime, I would definitely love to help out Mars.
Yeah, that's me. I do deep space. So what about Shivesh? What type of rocketry would you get to do if you get to pick?
Probably some sort of in-space propulsion. Something's just really, really appealing for small-scale systems. Like small scale, like for example, lunar transit systems, you could use pressure fed engines, you could use small scale turbo pumps. There's something very appealing to a very small scale system that, could fit on a desk, for example.
Yeah, that's actually, we're seeing a lot of interest in the transorbital as well, which is really kind of an interesting thing. Aditya, I don't think I've asked you. What's yours?
I definitely have to go with deep space. I mean, it's dope. I think it's really cool. I think like what NASA's done with the Voyager is really, really cool. And I mean, as Atharth said, it's unexplored. So why not explore it?
Yeah, that's so cool. And then I think Stathis, right? Your last. Which one do you want to do?
Yeah, I think I'd go with Mars, definitely, because Purdue already had the first man on the moon, so why not make it the first man on the planet?
You found a way to get that in. That's good. Awesome. You talk about deep space. So a friend of our PADT, a company called Kinetics, a woman that works there, Coralie Adams, she was the navigator for the Pluto flyby and the one that went to OSIRIS-REx. And yeah, so she drives the rocket, right? Not necessarily designs it, but it's pretty cool. And so she's living that dream all the time. And what's great about it in 2023 is she does it from her dining room on a laptop, right? Instead of the big mission control. It's pretty cool stuff. Yeah. What about you, Adam? I mean, you're doing air breathers mostly, but you like to play with the rockets. If you could go switch over to space propulsion, which would you do?
Oh, geez. I mean, I as a systems guy, I actually kind of appreciate the both the common elements as well as the nuances between all of them. On the one hand, there's something that's always been kind of cool about the sheer scale of orbital launch.
Yeah.
But at the same time, as we are seeing, the boundaries being consistently pushed and focus in towards getting to Mars and deeper space. I think there's also something pretty appealing about being involved with genuinely pushing the limits that way.
Yeah, and I still haven't made up my mind whether I like the Starship approach of all those engines that you have to control, or three big ones. I'm a three big engine guy, but like everything else, when I doubt SpaceX, seems to be working. So we'll see how it goes. So we'll go ahead and wrap it up. And the way I like to really wrap it up is for you guys to share with the listeners how to get in touch with your program. So we'll go ahead and start with you, Adam. What's the URL? And we'll put these in the notes as well.
Yep, our website is www.launchcanada.org. So you can find us there. We're on social media as well, so we're pretty easy to come across, and we got a bunch of videos of some of our past competitions and events and things like that on YouTube as well.
Very good. Shivesh, how about Toronto Metropolitan? What's the way to find your team?
Yeah, so our website is mock-tmu.space. That has all the information on our current and future projects. As well, we're on all sorts of social media, Instagram, LinkedIn, under the handle Mock.
Okay. And Alex, what about the Purdue teams?
Yeah, we have a website, PurdueScience.space, but I think our most updated information and pictures of what we're working on is the Purdue Space Program on Instagram.
Insta. And Grant, what about Luminosity for your lunar stuff?
Yeah, no, you can find Luminosity on Instagram is our most present social media presence at the Luminosity Lab, and then theluminositylab.com. You can see the wide range of projects we've got on there. There's pretty much something for anybody.
Great, very good. Now, Miles or Chris, I don't know which one you want to go. You can definitely find PADT at padtinc.com. But what about if you want to learn about Flownex?
Yeah, I think the same thing. If you go to that PADT website, or if you go to flownex.com, you'll find some good stuff. We also have a pretty active blog, so if you just Google Flownex blog, you'll find us.
You'll find us, yeah. And we also have a user forum they're trying to get people to sign up for. So you can definitely sign up for that as well. I wish you guys the best of luck. I think that. I guess you guys are the COVID generation, right? I'm not worried. You guys are getting it. This is great. I wish some engineers with 20 years of experience understood how to use this technology as well as you guys do. So congratulations on that, even the beginning of your education career. And thanks, Adam, for taking the time to create this event. I mean, these competitions really work, right? I mean, they really get people involved, and they really you hit the ground running out there in the industry. So
absolutely.
Yeah. Well, thanks for your time, everybody. Thanks for all those who are listening, and hopefully we'll do this again soon, and we'll talk more about what's been accomplished in the world of basically these rocket competitions in Launch Canada. So thanks a lot.